Here is a question that I'd like you to think about as we go through the contents of this video. While performing linear regression, we use mean square error as our cost function. This is what we tell our optimizer to minimize. Can we do the same while working with logistic regression? Can we continue with the choice of mean square error as the cost function? If yes, why? If not, why not? Another significant difference that's introduced by our switching to logistic regression is that our cost function changes. We now make use of something known as cross entropy. We will not dwell on the mathematics of cross entropy, we will just talk very quickly about the intuition behind it. Recall that the cost function is something that we've got to specify during the training process. This is required for TensorFlow to figure out how the optimizer should find the best values of W and B, the variables in our computation graph. In the case of linear regression, we used the mean square error. This was the sum of the squares of the lengths of all of those residuals. And the best fitting regression line was the one which minimized the value of that MSE. Now, in logistic regression, unlike in linear regression, we are dealing with categorical variables, and our measure of performance has to do with prediction accuracy. From the output of the logistic regression, we have predicted labels. We then need to compare these to the actual labels, which tell us whether Google went up or down in a given month. And then we calculate the prediction accuracy by tabulating all of the actual and the predicted values and seeing how often the logistic regression got it right. Cross entropy is a mathematical formula which is used to quantify how similar or dissimilar these sets of variable values are. Let's say, for instance, that the actual and the predicted labels look like the ones on screen now. In our example, actual and predicted values will always be either 0 or 1, but in general, the values of any variables drawn from any probability distributions can be compared. If the labels of the two series are in sync, then intuitively, those two sets of numbers are drawn from relatively similar probability distributions. This intuition is captured by a specific formula that's highlighted now on screen. This formula refers to the cross entropy, and we would like that cross entropy to be as small as possible. Now, you need not understand that formula, you need not even be familiar with the terms in that formula. All of this is abstracted away for you by TensorFlow, but that's the intuition. And likewise, the intuition between high cross entropy is if we have two sets of numbers where the labels are clearly out of sync. In such a case, that formula, the quantity which we called cross entropy, will be large, and that in turn will tell us that these numbers were not drawn from similar probability distributions. Once again, just a high level understanding of this is fine, because unlike in the case of linear regression, we will not actually code up a function to calculate the mean square error. Cross entropy is something which is abstracted away from us by TensorFlow. Let's now turn our attention to a few last little implementation details which will help while writing up the code. The first of these has to do with the one hot representation. When we made use of softmax activation, it meant that the output is going to come in the form of a vector of probabilities. Those probabilities will sum to 1, and there will be two elements, each corresponding to the probabilities of y being 0 and y being 1 respectively. Now, this is true in general anytime one is carrying out classification using a softmax activation function in the output layer. For instance, let's say we were performing digit classification where there are 10 possible output labels corresponding to the digits 0 through 9. There, the output that we would obtain would be in the form of an array. That array or one dimensional tensor would contain 10 probabilities. The highest of those probabilities would be used for the actual predicted label. All of those probabilities would sum to 1. So this is a general statement about any softmax activation. The outputs are going to be obtained in the form of label vectors with probabilities. Now, because the outputs of the neural network are obtained in this form, we also usually encode the actual values of the labels in something similar, and that form is known as one hot representation. Consider an example. Let's say that we have a label vector of true and false elements. The one hot label representation corresponding to this would have two dimensions. Effectively, we would now have columns which correspond to each possible value of the label. Here, there are two possible values, true and false, and so we have two columns. Every label in our label vector would now have 1 in exactly one of those columns. That column is known as the one hot value, and it would have zeros in all of the other columns. Again, this is a very standard form of encoding the actual labels when we are making use of softmax activation functions in the output layer of our neural network. And that's because the output of the softmax will emerge in a form which is similar to a one hot representation. Going from the label vector to the one hot representation requires explicit coding up. This is a simple bit of code which you shall see when we get to the drills. Going in the other direction, i.e., from the one hot label vector to the corresponding index of the one hot element, is accomplished using a function called argmax. We will end up using argmax a lot in the implementation in TensorFlow, so let's understand this function in some detail. Here's what argmax does. It takes in a vector or a tensor and it takes in a dimension. Then what it will return is the index of the largest element of that tensor in that dimension. Let's run through an example to make sure we understand what's really going on. Let's say that we use tf.argmax on a two-dimensional tensor. This is a tensor y. It has elements along dimension 0 and dimension 1. The indices, of course, of those elements arranged from 0 through 5. Invoking tf.argmax on this tensor along the first dimension will return the value 3, and that is because 3 is the index of the largest element along dimension 1. We will also make use of tf.argmax in this rather complex bit of code which you see on screen now. This is comparing the predicted and the actual labels. Let's break down what's going on. On the one hand, we have an invocation to tf.argmax. This invocation is on the actual labels. These are in the one hot notation. The second invocation is to tf.argmax on the predicted labels. tf.equal will compare the indices of the largest elements in the actual and the predicted label tensors and return 1 if they are true and false otherwise. Remember that the actual labels are in one hot notation because each month Google either went up or it did not. If it did go up, then the value of the true variable will be 1 and that of the false variable will be 0. And if it did not go up, then the reverse will be true. So the net effect of invoking argmax on the one hot label will be to return the indices of the one hot elements, which are either 0 or 1. That is as far as the first invocation of tf.argmax goes. As far as the predicted labels go, these are the outputs from the softmax activation. These are going to be predicted probabilities. So there will be two probabilities which will sum to 1. By invoking tf.argmax on these predicted probabilities, we are going to get the predicted final output. This will be true if the probability is greater than 50% and false otherwise. In other words, this is based on that rule of 50% which we previously spoke about. Let's work through a similar example, this time for digit classification. Here we will start with actual digits, which are numbers between 0 and 9. The one hot label vectors will now have 10 columns corresponding to the 10 digits 0 through 9. Of those 10 columns, exactly 1 will always contain the value 1, the other 9 will contain zeros. Again, this is the definition of the one hot representation because exactly one element is hot, it has the value 1, all of the other elements are 0. And in this way, we are guaranteed to have each row sum to 1. The one hot representation works for actual digits to go in the other direction to get the corresponding digit back from that one hot representation. Make use of the tf.argmax method. The actual labels are in one hot form, but the predicted outputs of the softmax are not one hot. Because softmax is going to return a vector of numbers, those are probabilities which will sum to 1. So for instance, maybe the probability of this digit being a 0 is 70%, that of its being a 1 is 30%, and the other probabilities are 0. In order to go from these predicted probabilities to our final predicted label, we are going to again invoke the argmax function. This will give us the digit or the index corresponding to the highest probability. This in a nutshell is why calculating the predicted accuracy requires two invocations to the tf.argmax function. One of these is on the actual labels which are in one hot representation. The other is on the predicted labels, which are not in one hot form but are probabilities that have been output by softmax. The net effect of invoking tf.equal on these two sets of return values from tf.argmax will be to give us a list of true and false values. Every true in this will correspond to a correct prediction, and every false will correspond to a false prediction. And it will now be a relatively simple matter to calculate the percentage accuracy. So, in summary, when we implement logistic regression in TensorFlow, we make use of softmax as the activation function in the output layer of our neural networks. The consequence of this is that we also need to encode the actual labels in one hot notation. And this in turn requires us to make use of the tf.argmax function in order to calculate accuracy. Don't be confused by the one hot notation or tf.argmax, it just comes with the territory while working with classification networks in TensorFlow. Let's come back now to the question which we posed at the start of this video. While working with linear regression, our cost function was mean square error. This was the mean or the average of the squares of the residuals in the regression. This is not something that we can use while carrying out logistic regression, and this has to do with the differing probability distributions of the residuals in a linear regression and the residuals in a logistic regression. Remember that in a linear regression, the residuals are normally distributed. If you were to take all of them and plot them, we would get a bell curve. In logistic regression, on the other hand, there cannot be normally distributed residuals because the residual values will all be categorical. In the case of binary logistic regression, for instance, the residuals will always be either 0, +1, or -1. There is no other option. The math behind the mean square error cost function will just not work with categorical variables in the residual series, and that's why we've got to make use of the concept of cross entropy instead. Cross entropy is a way of comparing whether two sets of numbers have been drawn from very different probability distributions or not.